So at the beginning of this chapter, we discussed the formation of alcohols via reduction, reducing the oxidation state. We can also use alcohols to go back to the aldehydes and ketones we started with via oxidation of alcohols. So this is the opposite of reduction. And I'm going to abbreviate these with RED, R-E-D for reduction, or OX for oxidation. So we could look at it from this perspective here. We take an alcohol, we oxidize it, and we end up with the carbonyl. And as we learned at the beginning sections of this chapter, we can reduce carbonyls back to alcohols. So they are opposites of each other. So we can look at a primary alcohol, and if we oxidize it, actually let's draw that out instead of writing primary. We can oxidize the primary alcohol to the aldehyde, and we've lost two hydrogens this way. The oxidation state is -1, and now the oxidation state is +1, so you see that we've increased the oxidation number, and we can oxidize aldehydes further to carboxylic acids, where we essentially add an O. So oxidation can be thought of as losing hydrogens or adding oxygen. And we see here as we go from an aldehyde to a carboxylic acid, we've added an oxygen, and the oxidation state here is +3. We can look at a secondary alcohol, and that can be oxidized to a ketone. And again, the oxidation state here is 0, and the oxidation state here is 2, +2. We could think, well, maybe we can do this with a tertiary alcohol as well. Remember that I said that oxidation is removal of hydrogens, and certainly we lost these two hydrogens in our secondary alcohol. There are no hydrogens that we can lose in a tertiary alcohol, so we get no reaction here. Alright, so let's look at how this might work. I'm going to take a primary alcohol, and I'm going to react that with an oxidizing agent, H2CrO4, which could be thought of as CrO3 and water. So we mix those together, we get chromic acid, H2CrO4. It is acidic, it is a powerful oxidizing agent. The Lewis structure looks something like this. We're going to gloss over some of this mechanism, but we're going to look more in depth at other parts of it. So that's H2CrO4. And when I mix a primary alcohol with that, you can see how I take the H and I take an OH off of the chromic acid, and I can now form a chromate ester. It looks like this. And I have one equivalent of water produced. And so what happens now, anytime we oxidize something, another molecule needs to be reduced, and that means another molecule needs to gain electrons. And if we set this up, if I remove this hydrogen, and I can use the water perhaps as my base, you might recognize this as a sort of E2 mechanism, where we have a beta hydrogen, we're forming a new pi bond between the C and the O, and we have a decent leaving group in the form of this chromium complex. And so that results in, you can see that our two carbon species here, we just formed an aldehyde. I just formed this new pi bond, and I have a reduced version of my chromium species. I can draw the lone pair on the chromium. We didn't have a lone pair before, now we do. So I have a new pi bond. I have an E2 process. The chromium is reduced. The problem is that this aldehyde is difficult to isolate when there's water around. And we do have water around because we formed water during the chromate ester formation. H2CrO4 is probably in water, so maybe it's more appropriate to show, aqueous. So there's definitely water around. So we can't isolate this aldehyde. So the problem is, I'm going to redraw the aldehyde down here. The aldehyde, in the presence of water and in the presence of more H2CrO4, can't help but get oxidized further to form the carboxylic acid. So I'm just going to extend this arrow up here. And that's via a very similar arrow pushing mechanism to the one I just showed, where we make a chromate ester and we would have some sort of E2 type elimination happening. We could also use, instead of H2CrO4, we could use Na2Cr2O7, sort of a different form of the chromic acid. Mix that with H2SO4, you're basically making chromic acid in situ in the reaction vessel, and there's water in there too. So this is another option that we could use instead of H2CrO4. Basically it does the same thing, and basically it's just another way of creating the H2CrO4 in solution. So we might say, well, that's great. If we have primary alcohols, we can convert them to carboxylic acids, but what if I want to stop at the aldehyde? So to produce the aldehyde, we have a special set of reagents. Here's pyridine. It's a non-nucleophilic aromatic nitrogenous base. CrO3 and HCl. When we mix those together in a 1:1:1 ratio, we produce this. The nitrogenous base collects the hydrogen, creates pyridinium, and that is a cation, and we produce CrO3Cl anion. The chlorine reacts with the CrO3. This is called, if I can spell it right, pyridinium chlorochromate. And because organic chemists don't like spelling all that out, as you can see, we abbreviated PCC. So you should know the abbreviation PCC stands for these reagents. There is no water here, so that's the important part of this. There's no water used to make it. There's no water present. This is sold as a salt. It's not dissolved in water. It's not dissolved in anything. We can use it without water, and that allows us to stop the previous reaction at the aldehyde stage. So now I can take my primary alcohol, I can react it with PCC, and I can do a 1 oxidation. Whereas if I were to take the same primary alcohol, react it with H2CrO4, I could not stop at the aldehyde. I would make the carboxylic acid. So now we have control over the outcome of the reaction. That is the organic chemist's goal. If I choose PCC, I produce just the aldehyde. If I choose H2CrO4, I could produce the carboxylic acid. Either of these reagents works with a secondary alcohol because there's only one oxidation that we can possibly do. So we could use either. There's really no distinction. Now you might choose one over the other because you have it on hand, or your boss says, I prefer to use that one because it's a little less acidic, it's more mild. That would be the PCC. Maybe you had to do, you needed the acid for some reason, so you might choose H2CrO4. The PCC is more gentle, but it also costs a bit more because it requires these three compounds mixed together in 1:1 ratio. You have to buy that from the chemical supply company. All right, so here's an experiment, or here's a thought for you. How could we make the aldehyde? Let's do it over here. I start with ethyl bromide. My goal is to produce acetaldehyde. How can I do that? Well, I know that I can take PCC, react that with ethanol, and I have the aldehyde. So how can I make ethanol from ethyl bromide? Well, that of course is from first semester organic chemistry. If we use a good nucleophile / good base, we have a primary substrate, so the strong nucleophile should act as a nucleophile, producing the alcohol, which we can then oxidize to make the aldehyde. And we can go further with this thought process. What if I reacted that with MgBr? What would I get? I would get something that looks like this. A secondary alcohol. What if I reacted that with phenyl? magnesium bromide. I would end up with this compound. Another secondary alcohol. So now we've just created a short synthesis that you should be able to solve at home or modify to create your own short synthesis. This would be a great quiz or exam question. How can I get from ethyl bromide to this secondary alcohol?